Multi-label classification of feedbacks. Introduction. In this work, a methodology is shown to automatically classify the feedback generated by a teacher to the activities sent by students in online courses according to the levels proposed by the Hattie and Timberlake model, to distinguish between messages that are in the task, process, regulation, praise, and other levels. Feedback. Feedback is a product resulting from the review and analysis by the teacher of the activity, contribution, or project sent by the students. It is the ability that the teacher develops when sharing specific information with a student about their performance in order to reach their maximum learning potential. The importance of feedback. Feedback is one of the most important factors influencing the student success. It is important for the improvement of a student's performance and the achievement of learning objectives, in addition to being the central part of the formative evaluation, so it must be constant, clear, timely, sufficient, and pertinent. It is the means that allows the student to identify what is needed to achieve success, according to what is expected of him. It helps the students to identify and solve the misconceptions with which performance is improved. Feedback research. Research on feedback focuses on trying to assess when feedback is effective to determine if and how to improve it. And effective feedback is one that allows closing the gap between current and expected performance of the student. Hattie and Timberlake feedback model. The levels proposed in the model are 1. Task level, which are comments that may be about a task or product indicating whether it is correct or incorrect, or includes indications to acquire more different or correct information. 2. Process level, that are comments direct to the process used to create a product or complete a task, direct to the information processing or learning processes that require understanding or completing the task. 3. Regulation level, that are comments direct at self-regulation, includes strategies to improve self-evaluation or confidence to commit more to a task. And 4. Praise level, which are comments direct to the self that are not related to the performance of the task. Based on this classification, Hattie and Timberlake point out that the most effective feedbacks are those located at process and regulation level, that feedbacks at the task level are only effective if combined with those from process level or regulation level, and that praise level are not significant for learning. In the literature, there are several proposals to determine the effectiveness of feedback. The Hattie and Timberlake propose 4 levels for analyzing feedback effectiveness. Multi-level classification. For the automation of feedback classification according to the feedback model of Hattie and Timberlake, multi-level classification techniques were used. The multi-level classification is a prediction task in which each of the instances has associated a vector of outputs instead of a single value, as is the case of the traditional classification. The size of the vector is adjusted according to the number of different labels in the dataset, where each element of the vector will be a binary value indicating whether the corresponding label is relevant to the example or not. Several tags can be active at the same time. Multi-label classification approaches. Multi-label classification can be worked from several approaches: data transformation, adaptation of methods, and assembly of classifiers. Transformation is based on transformation methods that applied to original multi-label datasets are capable of producing one or more binary or multi-class sets. Once transformed, traditional classifiers can be used to process them. Adaptation seeks to adapt existing algorithms so that they can deal with multi-label datasets by producing several outputs instead of one. Assembly combines adapted algorithms of data transformation methods to make predictions. Transformation methods. In the literature, there are several methods of data transformation. The ones used in this work are binary relevance, BR. It decomposes the multi-label classification problem into k independent binary learning problems. Classifier chains. It decomposes a multi-label classification problem into k-binary transformations just like BR. It differs in that the first classifier is trained only with the input attributes and the subsequent ones incorporate the output of the previous classifiers. Label power set, LP, it transforms the multi-label classification problem into a multi-class problem. Recall D, it divides the label space into equal partitions of size key, train a classifier LP for each partition, and perform the prediction by adding the results of all classifiers. Methodology, the methodology to automatically classify the feedbacks according to the levels of the Hedian-Timperley model followed in this work considers four steps. 1. Collection of data integration. 2. Preprocessing of TF, IDF, and calculation. 3. Classification. 4. Analysis and evaluation. Data. The methodology is applied in a case study to feedback generated by teachers to the activities of students in online courses of the law degree of a public university in Mexico was collected from the Blackboard Learning Manager system. The dataset contains feedback written in Spanish generated by teachers who publish them through the task review tool in the learning management system. The dataset is made up of 11,013 feedbacks from 121 online degree courses in law. The average number of words in each feedback is 77. Each feedback was manually classified by the instructional design experts who followed the model described by Hedian-Timperley to locate each feedback at levels NT, NP, NR, NE, and NO. Training and testing sets. There we have Table 1, distribution of feedback in multi-label training and testing sets. Each feedback was manually classified by instructional design experts who followed the model described by Hedian-Timperley to locate each feedback at levels task, process, regulation, price, and other. At the end of the manual classification of feedbacks, a multi-label data set was obtained in which each feedback has a vector of 5 elements associated with it, corresponding to the label task, process, regulation, price, and others, where each element is a binary value indicating whether the corresponding label is relevant or not. Several labels can be active at the same time. The multi-label dataset was divided into two sets, training and testing, containing 66% and 34% of the feedbacks respectively, chosen randomly. The distribution of feedback classified by each level is shown in Table 1. Characteristics of multi-label datasets. Table 2. Characteristics of multi-label datasets. The characteristics of the multi-label datasets for training and testing using this work are shown in Table 2. Cardinality counts the number of relevant mean labels for each instance in the set of data. Density refers to the cardinality normalized by the total number of all possible labels. Mean IR obtains the maximum radius of unbalance, that is, the radius of the most common label against the rarest. This Campbell value measures the concurrency between frequent and rare labels. Pre-processing and calculation of TD-IDF. The feedback from the test and training sets were processed as follows. 1. HTML, CSS codes were removed. 2. Cleaning methods are applied to obtain only the words and digits of each feedback and digits. Web addresses and file names were replaced by the identification keys. 3. Feedbacks were converted to small letters to make comparable words with the same meaning. 4. The limits of each of the words were obtained. 5. A spelling check rule was applied that uses the Levenshtein distance for words with frequency less than 10. 6. Stop words were eliminated. 7. Truncation was applied. TF-IDF calculation. Once the preprocessing stage was completed, the feedbacks were transformed into the term document matrix representing the frequency of each word in each feedback. The TF-IDF value combining the term frequency and its inverse frequency of feedbacks was calculated by multiplying the local frequency weight of each feedback by the inverse weight of the feedback. Classification. This stage consisted of applying data mining algorithms to train multi-label classifiers to learn from the test sets that contain the manual classification of feedback. In total, 16 multi-label classifiers were trained. For each of the data transformation methods, binary relevance classifier chains, label power set, recall D. Rebase algorithms were used for each data transformation method. Support vectors, machines, random forest, logistic regression, and naive Bayes. Analysis and evaluation. For each multi-label classifier created in the classification stage, it was analyzed and evaluated how well they did the task of locating the feedbacks according to the levels proposed in the Hedian-Timberlake model. The feedbacks from the test were passed to each multi-label classifier to predict the levels at which the feedbacks were located. The result was a set of predicted labels of each feedback. To measure how well the feedback is located according to the levels of the Hedian-Timberlake model, each multi-label classifier to commonly used metrics were adopted. Accuracy F1 micro, F1 micro, Hamming loss, subset accuracy, ranking loss, average, precision and coverage. These metrics compare the set of predict labels with the ones you should actually get contained in the test dataset. Results. The results obtained are shown in Table 4, which shows for each data transformation method VR, CC, LP, and RACL-T. The metrics evaluated using the base algorithms SVM, RF, LR, and NP. It is observed that for the accuracy of the classification accuracy, the base algorithms that best classify are RF and SVM, as they manage to classify well 7 out of 10 instances compared to NP, in which less than 60% of feedback runs well. Regarding the precision and exhaustiveness of a F1 macro, it is shown that the VR and the CC approaches are the ones that best classify. The base algorithm that gives the best result is RF. It should be noted that the values were affected by the imbalance of the classes. For the precision and completeness that considers the level of imbalance F1 micro, it is the VR approach that best classifies with the SVM algorithms. The RF algorithm also shows a good classification in comparison on what is achieved by the LR and NB algorithms. It is detected that a high value is reaching the detection of labels that are relevant, where 8.5 out of 10 predictions marked as possibly are correct. For Hamming loss, the classifiers using VR and CC are the best able to classify feedbacks when using SVM and RF algorithms with only 8 out of 100 misclassified instances. For the 0-1 metric, it is found that using CC with the RF algorithm, the best classification is obtained by only having 2.8 out of 10 misplaced feedbacks when considering the complete set of labels. For the ranking loss metric, it is observed that for VR, CC, and LP, it is the RF algorithm that classifies the best, followed by the SVM algorithm. For the ABG precision metric, it is the RF algorithm that classifies the best. SVM also shows values very close to those of RF. For the coverage metric, the best classification is achieved with VR and CC using the RF base algorithm. Radial graphics, gráficas radiales. In the radial graphs of Figure 1, each vertex corresponds to an evaluated metric, and the points that correspond to a single multi-label classifier are connected to form a polygon. The larger the area of the polygon, the better the classification. It is observed that for binary relevance, classifier trains label power set and RACL-D, the support vector machines and random forest based algorithms classify better. Conclusions. In this work, a methodology is applied to automatically classify the feedback generated by a teacher to the activities sent by students in online courses according to the levels proposed by the Hedi and Timberlake model, to locate them at the NT, NP, NR, NS, and NO levels. For multi-label classification approaches are compared each with 4 base algorithms. The results show that the best multi-label classifier is obtained using CC with the RF-based algorithm when reaching the best values in 5 of the 7 metrics analyzed. Using the RF and SVM algorithms as the basis for the RB, CC, LP, and RACL-D multi-label classification approaches allows to obtain better classification metric values. The NB algorithm shows a low misclassification compared to RF and SVM. As future work, we will try to test whether the classifiers work with feedback obtained from online courses in other areas of knowledge. It will be explored whether the values of the classification metrics can be improved by using different tokenization configurations, bigrams, trigrams, etc. References.